quick table. And the table basically saves a lot of time. So we're going to set up a table. We're going to call one column D. We're going to call the next column I. Ready? D here stands for differentiate. I here stands for integrate. So all you have to do is use ILATE to pick up which one you're differentiating. So when I use ILATE now, remember ILATE. This here is algebraic, so this is A, and this here now is exponential. Which one comes first? Algebraic. So I'm going to set my x squared to differentiate, and I'm going to set my e to the x to integrate. Now, all you're doing is just differentiate until you get a value of 0, right? So differentiate x squared until you get a value of 0, integrate this continuously. Ready? So when I differentiate x squared, I get 2x. When I integrate e to the x, I get the same thing. So that's very easy for us. When I differentiate 2x, I get 2. When I integrate e to the x, I get e to the x. When I differentiate 2, I get 0. So we're finished with the table here, right? Now, this is your answer. Ready? Pay attention closely. So what we're going to do, we're going to go slant with it. So I start here, and I'm going to go slant, right? And I'm going to use a value, a positive value here. I'm going to go again slant, cool, and I'm going to use a negative value here, cool. Then I'm going to go slant again, so this should be e to the x down here, right? Because you were supposed to differentiate and integrate it again until you get 0. When I go slant again, I'll just get a positive. So the idea about the slants is you're going to take positive, negative, and you just alternate it. Ready? So the answer, using the tabular method, x squared e to the x dx is actually going to be, so positive of x squared e to the x, so x squared e to the x. Then I'm going to have minus 2x e to the x, so minus 2x e to the x. Then I'm going to have a plus 2e to the x, so plus 2e to the x here. Then there's nothing else, so we're just going to drop our constant of integration, which is a plus c. So again, once you know the tabular method, and once you can identify which one to differentiate, which one to integrate, then you're basically on your way to answering the question. And everything, every differentiation, every integration by parts question just requires you to be able to pick up which one to differentiate, which one to integrate, and you're good. You're very much on your way. So before we end, there's one particular example that I'd like to demonstrate that it doesn't always go to 0. So if you had a trig function, what you'll realize is that the trig function will basically oscillate. So it will oscillate between sine and cosine, and it will just change value. So for the final example for today, I'm so sad, but time is up. So for the final example for today, I'd like to show you guys an example. It's going to be a little bit hard, okay? You have to pay attention. It is the integral of e to the 2x times sine of x dx. Now, again, whenever I get questions with integration by parts, I write up my ILATE so I know where I'm working with. Ready? This here is exponential, so this is e. This here is trigonometric, so this is t. Which one am I going to set to differentiate? I'm going to set sine to differentiate. So that's beautiful. Ready? So I know which one I'm differentiating. I know which one I'm integrating. So set up your table and start doing that. All right. So I know that I'm differentiating sine. So I put my sine x over here. I know that I'm integrating e to the 2x. So I put my e to the 2x over here. All we're going to do now, ready? Because it oscillates, it's never going to stop, right? So you'll continue on and on and on forever. But there's a way to get it to stop. Ready? You're going to repeat it until you see sine x here and e to the 2x beside each other. It doesn't matter what values are attached to them or whatever sign is attached to it. As long as you have sine x and e to the 2x, then that's where you're going to stop. All right? So let's differentiate and integrate. So when I differentiate sine x, I get a cosine x. When I integrate e to the 2x, it gives me e to the 2x. But now, using the chain rule that we did before, you have to divide by the differential at the inside. So that's just going to give me a half e to the 2x. That's good so far. Let's come down more. When I differentiate cosine x, what's that going to give me? That's going to give me minus sine x. Cool. Now, when I integrate half e to the 2x, I'm going to get, that is going to give me a quarter, because when you multiply by half again, it gives me a quarter. E to the 2x does not change. Now, if you look here, you have sine x and e to the 2x beside each other. That's where you're going to stop. Don't go any further, right? Cool. So what we're now going to say from this table, it tells me that the integral of sine x. Okay, so when we were integrating e to the 2x from the chain rule from before, right? It's basically an application of the chain rule that we did. So this would be e to the x would be the outside function, and 2x would be the inside function. So remember the rule said that you integrate the outside function, that will give me e to the 2x, because e to the x is the overall outside function. And the inside function here would be a half. So divide, inside function would be 2x rather. When you differentiate that, you get 2. So you're going to divide by 2, that will give me a half. If I repeat the process, this will give me the same thing over and over again. So when I integrate a half e to the 2x dx, it's just going to give me a half times a half e to the 2x, which will give me a quarter e to the 2x. So Jodian, what we were doing, we were applying the chain rule there. Does that clarify for you? All right, no problem. Thanks for asking. All right, so let's work. So what we started with was the integral of, let me just write this better. So we started with the integral of e to the 2x sine x, right? And if we use our tabular method now, ready? Remember we go slant way. So we're going to go slant. So that's going to give me a plus, the first slant. And I'm going to go slant. It's going to give me a what? A minus. But here's the thing now. You're not going to go slant anymore. Whenever you see them repeating beside each other, you go straight across. And this straight across now is going to give me a plus there. So everybody see that? So instead of going down anymore, it's just going to repeat over and over and over again. So you can just go across in this case. All right. So let's write out the values. Ready? So this now is going to give me a half. So let me just write the half at front. So a half e to the 2x sine x. Cool. Then I have a minus now. Then it's going to give me a quarter e to the 2x cosine x. Now, I know that in the first example, what we did was to just write out the values, go down the table and so forth. But whenever we have this case where we actually have to go across, when you go across, you have to integrate going across. So when I'm integrating now, this is minus and plus. So minus and plus will give me an overall negative. And I'm going to integrate, guys. Ready? Integrate a quarter, so I can bring the quarter at the front, a quarter, e to the 2x sine x. So again, when going across, you integrate, all right? But when going slant downwards, you can just take whatever value it is on right. Cool? Now, the reason why we did this from the get-go, if you look, this is the integral of e. Let me put my dx's here, by the way. This is the integral of e to the 2x sine x. This is the same thing. So I can group those things on one side of the equation. So if I carry this over here now, guys, it's going to give me a quarter e to the 2x sine x dx. So that's a quarter, right? Plus e to the 2x sine x dx is going to be equal to, now, you probably don't pick this up. What I'm going to do on this side is to factorize, right? So I'm going to factorize everything that's left behind. Let me not do everything in one step. So I'm going to write them out. So half e to the 2x, then sine x here. Then I'm going to have minus a quarter e to the 2x cosine x. All right. Now, if I have a quarter of something plus 1 of the same thing, then that would give me 5 over 4. Because a quarter plus 1 is 1 and a quarter, which is just 5 over 4. Yeah. So we have 5 over 4 e to the 2x sine x dx is going to be equal to, now, remember the promise I was going to factorize. So if you realize there's a common e to the 2x, don't it? So I'm going to factor that out to the front. And then I want to factor out what's happening here with the numbers. So this is a half and this is a quarter. So when I factor half and a quarter, the LCM here, well, the highest common factor rather, is going to be a quarter. So I go factor out a quarter, right? What's going to be left on the inside? A half divided by a quarter is 2. So it's going to give me 2 sine x. Then a quarter divided by a quarter is just 1. So minus cosine x here. Cool. Now we're almost finished. Remember, this is what we want to solve for. Just this portion here, well, this entire differential, right? That's all we want to solve for. We don't care about nothing else. So what we really and truly have to do is to basically get rid of the number in front of it. So when I do that now, I have 5/4 currently. To get rid of it, I'm going to multiply by its reciprocal. So multiply both sides by its reciprocal. Probably I should change my color here. So multiply both sides by its reciprocal. It's going to give me e to the 2x sine of x dx is going to be equal to 4/5, because I'm multiplying by the reciprocal, times a quarter e to the 2x times 2 sine x minus cosine x. And then when we do that now, you'll see that the quarters will cancel out. The answer is e to the 2x over 5 times 2 sine x minus cosine x. So for the two examples that we did for integration by parts, one example showed you where you would differentiate to a value of 0, right? The next example showed you where you would differentiate continuously, you will never stop. Whenever that is the case, more than likely it will happen with a trig function. Whenever that is the case, you'll always look for where you have the starting points beside each other. Whenever that occurs, that's where you just go across. All right. So guys, I hope that I was able to help you understand integration a little bit better. As I did mention, it's a lot to do. We still haven't touched what I had planned for, because I had planned for us to do the definite integral and some other stuff. But time is out. But I really, really do hope that I was able to help you. I really do hope that you learned something new from today. All right, so that's it.
All right. Thank you guys for joining. We're going to end the video right now. So, all have a blessed day and goodbye.